All right, today let's look at chapter 10. It's called function templates. And we have alluded to function templates when we talk about last chapter about functions. And we noticed there's a bunch of duplication of code, um, almost identical code, but we're dealing with overloaded functions with the different types. And it's not an ideal way of writing your functions where you have a lot of duplication. So there's a mechanism to solve that problem, which would be using templates. So let's take a quick look at a simple function template. And let's say we have a function template that is to compare two values and see which one is larger. And as you notice here, there is a keyword template, and the template takes parameters in this angle brackets. And in here, you have another keyword called type name. Uh, that means whatever follows is a type name, name of a type. Now over here, you could also use class. That means the same thing. But I kind of prefer type name because class might indicate normally can be understood as actual class types. But if you use the keyword class here, it doesn't mean it's just to be class types. It could be fundamental types, right? So, uh, you know, type name here or class, this is kind of equivalent, but typically type name would be preferred. And so this is here we indicate this T is a parameter to the template, and this is a type. And this type you can use it in the basically the function, header and body, right? It can be a return type. It could be the parameters to that function. And as you see, besides that template keyword and the template parameters, the rest of it looks like a normal function definition. Okay, so that's what makes this a template is really this part where we have extra parameters that are sort of elevated into the template instead of just a regular function parameters. And this allows the compiler to generate or instantiate specific functions. So this by itself is not a function definition. It's it cannot be used directly in your code. So when you have a specific function call, and that is the time the compiler will try to find the template that's going to match the function you're trying to call, and then instantiate a particular function that matches that particular function call. And of course, in that instantiation, the type T is determined. Okay. So in your executable, basically only the instantiated functions exist. The template no longer have a meaning, well, no longer have a role in the actual executable. It is used in the compilation process. And then when you actually invoke a function that's sort of coming from a template, you can actually specify the template parameters. When you do that, that is when there's ambiguity. Then you need to specify. We're going to look at an example that you will see how that's done. But for right now, there's another thing about template specialization basically it's not necessarily a very useful feature, but what you do is you may instantiate a template by specifying the parameters specifically. Let's say this is a a specific template that will have the parameter instantiated, and this and then you may have a, let's say the reason you do this, maybe you have a sort of a slightly different implementation than the generic one. That may be a reason to do it, but then if that is the reason, you may as well just overload the function or have an overloaded function template. Basically, something that's slightly different. Um, there's really no, there's not a whole lot of usage of specializing a template, and yeah. So, but want to mention this here and for completeness. Now here, you'll see there's you can do certain things. For here, for example, when you specialize a template, when you specialize, it means that you're going to actually uh, have the template type sort of a specified, and then so you have that specific template. Um, when you do that, by the way, this is already means that you have a particular version of the function that's instantiated. Essentially, this is asking the compiler to generate a function out of this template for the parameter type double. Now, this double here, you specify in this argument parameter here, and also as part of uh, the parameter for the template, and then you put it over here right after the function name. Um, and this seems to be redundant. See, this actually instantiates this particular function, right? Function with a double type. So it's is instantiated, and that will is ready to use. Um, and then you may also omit that particular type name in this particular specialization, because the compiler can figure this out, can deduct it, because you have specified the parameter as a char, and this t is obviously the same as the template parameter t, so you don't have to specify it. And then this empty angle bracket also can be just omitted. You don't have to have the angle bracket, by the way. So here's another example. And this is instantiates to f with a parameter type int and then parameter int. So this is equivalent. And there's a slight difference between a template and instantiated template or specialized template in terms of including a module. Let's say you have this. Here's the thing about the. Let's say you put this in a header definition, and then you cannot just say you have a sort of a prototype of a template function in the header, and then you implement the body in a, let's say a source file. You separate them. It's not going to work unless you also include, basically you have to include the source code of the definition of the template function template in. That needs to be included. The whole thing needs to be included because the compiler needs all the information about the template definition in order to instantiate the functions at the place where you're calling. So, but then if you have a specialized template like these are just like practically they are just like a regular functions. And then with this, you can essentially have a you can have you can separate the implementation from the prototype if you want. So there's a tiny little difference here, but not that you're gonna necessarily need that at this point. But I just want to mention that. And then, as you notice, we have the type parameters where you have a type T. We're using with the keyword type name, indicating that is a type. But you can also have non-type parameters for templates. Non-type parameters means you can typically what's allowed here are the fundamental types. Um, Not necessarily just fundamental types, but or maybe the equivalent of fundamental type. That's kind of what you see most common. Technically, you can use other things, but they're not common. There's not a whole lot of purpose of doing that. So you have noticed, for example, the standard array container that it has an element type, but also has the size of the array, because the fixed size of the array as the template parameters. So that would be an example. Here we have a simple example. Let's say we have two non-type parameters that are integers. You have a lower and upper. And this is simply to check if a value is within the range, basically in between lower and upper. Uh, Again, just a toy example to illustrate. And so you can use those non-type parameters in your template function template definition. And not only this, you can also specify like unknown number of parameters. You have 0 or more of the same type, and that would be called a parameter pack. So here we have a parameter pack. Well, actually here, this really is saying we can have any number of types. They are, the type name indicates this is a type, and then with the 3 dots in the middle, and that indicates we'll have a parameter pack. Basically, you have 0 or more types, and then you can use that parameter pack in the function declaration, the function parameter like this, because this itself is a type, and then use dot dot dot. Obviously, you can have a parameter name like arguments or whatever following it if you want to. So this is a simple example here, and we don't have implementation, just to show what you can do here. And so if you invoke this function, this is a that you have an instantiated function. This, when you call this with this, now we have 2 parameters, knowing that you can have any number of them. And so you have a char, you have an int, right? So this basically will expand into a void f of char and int parameters. Okay. And this one, here we have a double. So very simple, you will expand. And this ts dot dot dot, it's like this will automatically expand into a double in this case. All right. Now here's another example, because the form uh, the way to specify a fixed size array is a little bit different when it comes to parameter pack. So let's say we have a parameter pack ts, these are the types, and then we also have another parameter pack of integers. We call that n. And when we use these 2 things, we could have a function template g taking parameters of any number of arrays, and the arrays types are, are specified as ts, and then notice there's a dot 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 after there's an ampersand. So normally you have a regular function, you can capture an array without the dot dot dot, but you still have to remember you have to use parentheses here to indicate you have a reference to array, right? Not an array of references. So that's the difference here. So you have a reference to an array. Now here we're basically saying any number of arrays, 0 or more. And the array size is n. Well, you notice n is also parameter pack, because this type and the size, they're both parameter packs, and they need to match. So, for example, by the way, here we're specifying the template parameters, because to help compiler determine what those element types are. So there are cases where the compiler cannot determine, and then you have to specify them like this. So here we actually have two arrays. Remember, this is the C style string. It's essentially a char array and of size 2 in this case, because remember there's a null terminated, there's a null character in the end. So there's actually two characters in there. There's a and there's a null character. So the size of this array is 2, and then you also have n, which is obviously a integer array of size 1. So uh, this particular parameter will be expanded. The parameter will expand into these two, um, basically into these two array types, right? And there are references. Okay. And then you might think, okay, what is the usage of a parameter pack? And here's a simple example here. And this also I want to introduce, there's one more type of parameter you can use in a template. So you see here, you still have the regular type name. These are just the type parameters. But you also have another thing. This is another parameter. This parameter, we'll call it container. This parameter, okay, you recognize the type name. This is also a type, but this itself is templatized. Okay, so you see this thing before this. You got template, angle bracket, type name, dot, dot, dot. This is telling the compiler this container itself is also a template. So this particular parameter is called a template parameter. Okay, well, in fact, the standard says it's a template parameter. It's pretty confusing, but you've got the type parameters, non-type parameters, also template parameters. Okay. Now this is saying, well, this container should have this kind of a shape. If this has to be a template and this template has this kind of shape, the shape, well, basically means that we have, by doing this parameter pack means there's a 0 or 1, 0 or more types, right? And it will separate this into, like, we have a 1 and a plus a parameter pack. That means at least one parameter. That's what we're trying to specify here. This container is a template which has at least one template parameter. And so then we have this. This is what we're trying to do, is we're trying to just print out the values of a container. We're talking about the standard library containers like array, vector, that kind of stuff, right? So here we have a reference to a const container, and we can have this template arguments specified for the container. And then inside the body, actually, we're not using those types, the arg0 or args, rest of the args. And we're essentially just using a range-based for loop. So all the containers, standard containers, support this range-based for loop because there are ranges. And this allows us to print out a value this way. Now, there's one little thing here I mentioned. This is for, suppose you have a map, a container, in the standard library, you have a map, which is a key value pair. It's not just a single value. The value actually comes out of as a pair. When you do a range-based for loop here, this is actually a pair. And so in order to be able to use the stream insertion operator to output that pair, and so what essentially will now will support. Now we're going to look at this actually more next week, I believe, about the parameter operator overloading. This is actually overloading an operator. Just for now, for your information, but we're going to talk more about this. This streaming insertion operator, we're going to say this cout, the type of cout that's defined is an object defined in standard library, is actually of a type OStream. Okay. For input output, the OStream is an abstraction type, and that's in the standard library, of course. So we are essentially saying, we're going to also be able to understand how to print out a pair. This is the type for pair. The pair takes two template parameters, and so this itself, this function, is also an example of function template, right? We'll have two types here, T and a U. So the pair, it has two values. They may be different types, and maybe the same type, but they most, could be different. So you have two types. And so we want to print this out. Essentially, what we're doing here is that we'll print out with a square bracket and the first value and colon second value. This is what we want to do. So by supporting this and this cout, we'll be able to output the pairs coming out of the maps. Okay. And we haven't really used the maps right now, but I just want to mention this in the context of a template, function templates. But I'm sure we're going to use the maps fairly soon. We'll introduce that. Okay. Now, we have used the auto keyword in various different places. You may have noticed. And that auto usually is used for type deduction. When you declare a variable, for example, right? You assign something to a variable and then you don't want to type out the variable type, and then you can use, just be lazy, use auto. That's fine. Mostly it will be okay, but that's not really the most common usage of auto. Now, before we talk about, what role of auto is in our template, we're going to see it in a second. So one thing to note is that the compiler will try to deduct arguments for a function template. Now let's say we have a function template trying to convert from one type to another. So we have two types. There's a from type, there's a to type. And here, so if we have an example here, we call convert and then we specify the template parameter int. So we're trying to convert. This is the target type. This is really here's the thing. You see we have two types here. We only specify the first one. So which is the two, right? It goes by the order. And the second one is not there. That means the compiler will figure it out. How does the compiler figure it out? Because look, the from is also specified here as a function parameter, and that's D. And D we know is a double, so it knows that the second parameter must be double. That's why it basically calls this function, this particular instantiation of a template. Now, similarly, if you specify char as the single type in this function template invocation, then it will deduce the second one. Okay. Now, here's another example. Actually, on the left-hand side, this is actually a pointer to a function. And this particular form, this is a pointer to a function that's returning int, and it takes a parameter float. And so this converts, and because we're having this pointer to convert, and what we kind of already specified what this pointer, function pointer type is. And so obviously the compiler can already figure out what kind of convert function it needs to use. So essentially, it's converting from a float to an int, okay? And then the return type deduction. So we'll talk about auto, and we'll have used auto in a variable type deduction, but also here when it comes to function template, we can deduce, let the compiler deduce the return type. Sometimes it's convenient, sometimes it's actually necessary. So here's an example right here. We have two types as a template parameters, T1, T2. We're taking two parameters in this function, larger, and we're comparing them. Okay. Now, what is the return type? Well, you see, depends on which one is larger. This returns either A or B, and there are different types, right? So this auto will be able to figure out, here's the thing. With this expression, by the way, it will not, the answer to that question, what is the type of this expression? It is, well, it would be either a T1 or T2, not because we have this conditional operator here that's saying, well, we either returning the type of A or a type of B, and that's not really how it's done. And when it does this comparison here, A greater than B, it will need to convert one of them to the other to basically determine what's the common type. If you have an int and a double, it will convert the int to double, okay? Because the double is has a bigger range, and then we'll do that, and then say the double is the common type of int and double, and then um, and it basically makes a uh, temporary variable somewhere, and then that holds on to that converted double. Then it will evaluate this, or the return type will be double. Okay, then what if we're passing, here's one thing though about this auto keyword. This is a placeholder type. This placeholder type, it does not indicate, this already always evaluates to a value type. It doesn't, it's not a reference, it's not a const reference, a reference to const, right? It's, and those things are extra. So if we are passing in, here's the thing, you know, if this A or B, there are like, let's say they're a container, they're like a vector with many elements. And by doing this, it will incur some kind of a copy of A or B, depending on which one is bigger. And it will actually do a copy, and it will not be very good, okay? So in order to avoid that copy, if they're actually indeed vectors, right, you got the reference to const vectors, you don't want to just return a vector type. You want to return a reference to const, right? Here we're returning either A or B, reference to const vector. So the auto will not do it, okay? So then you also want to auto to determine, in the case of an int and double, you don't want a reference to const in that situation. A copy is fine for fundamental type, okay? So what do we do? The solution is to use declared type keyword. There's declared type keyword of auto. Declared type means, again, that means declared type. This is going to give you the declared type of this expression that will be returned. And it turns out that if these are T1 and T2 are vectors, and we know A, B are actually reference to const vector, right? And then this the type of this expression will be a reference to const vector, okay? And then that type will be retained as is, because we are saying this should return the declared type of whatever that type is. So that will not modify, you know, the reference type into a value type, like by making a copy. It will just use that as is. So that is again, you may not see this very often, but there will be occasions you may want to use it. Now, there's another thing called abbreviated function template. At this point, the compiler support is rare, actually. This is sort of more of a syntactical sugar, what we call. It's not, it's equivalent, just like you're saving some typing. But then what you're getting also is maybe as less clear, is this a template? So yeah, you're saving this line here. You're using this auto keyword in the parameter of the function. This is equivalent to a template where you have one parameter for the template, which is just some unnamed parameter type T. This is equivalent to this. And I just want to mention one more thing here. And this is a C1. You see, okay, what the heck is a C1 auto? Now, then you recognize this is going to get translated into this particular template. Instead of a type name, you have a C1, and then before the in front of the type T, and this is actually concept. And actually, the last week we're going to talk about concepts, and this is basically here just kind of why we use concepts. Here, we're in this body here, we're comparing A and B. Now, why do you think this A and B are comparable? Why would this operator work between A and B? And here, there's nothing that says these are the things that you should be able to comparable. So there needs to be constraints on these types to make your template type safe. You cannot pass the things that will make this invalid because they cannot be compared, right? this operator is not defined for that particular type you pass in, then that's not good. So there are, before we have the concepts, there are some pretty sort of complicated ways of enforcing the putting constraints on the types of the function template, specifically using the static assertions. Static assertions are the assertions that you actually run during the compile time. But then that has been simplified with the concepts. So that is something we'll talk about last week. All right, summarize this chapter. A function template is a parameterized recipe to generate overloaded functions. Yes, so see, same name, right? But then different parameters, hopefully, because the parameter, you have different types, or maybe you have a different, yeah, typically you have different types as arguments. So they actually, the result of having a template is it's going to generate many overloaded functions as needed. If your program has the invocation, let's say for with an int, which is the template parameter, that will be generated, but it will not generate for other types that has not been used. And a function template parameters can be, there's three types of parameters you can use in function templates: types, non-types, and template parameters. Okay, we have seen an example of template parameters. A function template can be overloaded with other functions or function templates. And there's no difference here as we talk about the function overloading, and that's the same thing applies. You can define multiple function templates with the same name as long as there's something that's a little bit different. The placeholder types, auto, reference, that kind of stuff, they can be used in the function parameters. When you do that, then what you have is abbreviated function templates. They are no longer regular functions. And this particular feature has not been supported by all the major compilers. For example, the MSVC doesn't support it yet. So we can't demonstrate that. All right. Let's take a look at programming example. Now, this example is, we're seeing this declared type of auto. Remember that we're talking about, let's say you're comparing two vectors. And when you compare the two vectors and then the result, if I hover over this larger function here, you see this, the pop-up shows this return type of this instantiated template is a reference to const vector, okay, just as we just explained. And then if we invoke this template with the string arguments, and then we'll deduce the return type as, in this case, it's a const string. All right. So the funny thing here, as you see, the first argument is a const string. The second argument is it's a reference to const char array, right? And because it's a C-style string. Now, when you have these two things together, you're doing a comparison here. This expression is going to take, the compiler will determine what's the common type between these two. And they realize you can convert that C-style string to string, but sort of not the other way around. And then you will basically use that as the resulting type, and that is the return type of this larger, as you see here. Okay, but not only this, it's also const, because both of the arguments are const, and that is retained because we're using declare type. If we did not use declare type here, it would have been just string, not a const, not a reference. Those things are dropped. And here, this we have an int and double. The common type between int and double is double. When you're evaluating this conditional operator, this expression here, the resulting type is going to be double. And since both are const, reference to const, and then there's just a fundamental type here, because the fundamental type, and then it does not need a reference to const. It essentially just results, the return type will be just simply double, and that the compiler determines this is sufficient. Now, if the resulting return type is not what you want, right, and then uh, you can write a different template. You have a choice to make that determination if you want. Now, take a look at another example where we have uh, this array. We can capture an array in the this is almost like what you see in the standard array, the standard array in the standard library, that's a container, and this you have a element type, and then you have the size of the array. This is a fixed size array, and then so the way you can capture this in the parameter of the function is that, remember, this is a reference to, so this is a reference to const array, and with the size of the array attached with this square brackets here, okay? And the implementation is fairly simple here. Essentially have a for loop and to calculate the sum and then divide it by the number of elements. So you can run this and then just look at this. Now here, if you assign this array to a pointer here, like what it shows here, let's say if I uncomment this, and it's going to show an error because it says no instance of a function template average matches the argument list. The argument types are pointer to double. So the pointer to double, it cannot deduce the size of the original array anymore. That size information has been lost, okay? Or yeah, basically in this case, that's what's happening. So that doesn't work. Now, previously we'll talk about, remember that in chapter 9, we'll say, okay, there's a, remember that largest function we have overloaded multiple times and we use a span, okay? That's the vocabulary type that we should use. Now, problem with this is we got 3 almost identical functions. The only difference is the type within the span, that the sort of the parameter, the type parameter of span. Here we have a double, and then we have int, we have a string view. So that's not very good. If you look at the body, it's pretty much the same thing. It's very much the same thing, right? There's really no difference. You see that? So why don't we consolidate these 3 overloaded functions into a template, right? So let's see if we can make this work. Here we have a sort of a prototype, the declaration template and type name. So the return type is going to be T largest. And so we say this is data, okay? This should capture all these 3 forms of overloaded function here, largest. You got the const double, const int, const string view, right? And why not just, extract, turn that into a template, right? This should, let's see what happens here. Now the body is fairly straightforward. If I copy this, and then I'm just going to change this. This is going to be just type T. That well, the words. Okay, this is data. Okay, and then this is one particular data item. Let's say this is one single value. Let's call this max. Okay. Right, this is equivalent to before we did some renaming because this is more generic. It cannot say this is the word unless unless we're dealing with a string. Okay, we just generalize that. And this is essentially equivalent to all the 3 different forms. Now, Will this work? I don't know. I don't see any error from my IDE, but let's see. Let's see what we'll get. Let's compile this. Okay. Well, we see some errors. Let's take a look at the very first error. This is line 30. Okay, right here. Excuse me. It says no matching function of a call to largest. And as highlighting this function, there's a problem because it cannot find a matching function. Like, where's the function? I see some template, but I can't find it, can't match it. Well, it turns out, so here we got an array of const doubles, right? And the problem is this type is not being deduced, so we can put it into the span. Because actually what we're doing here, we're not really passing this array as is. We're actually constructing a span out of that array, right? So when this is the situation, it needs to do a conversion from a one templatized type into another templatized type. It can't really figure out that the element, that this particular type parameter, whether they are matching or not. But here we're not really saying they should be matching because we're not really capturing the information of the original data you're trying to pass in. We're trying to turn that into a span. So anyway, so here we need to give the compiler help. We say, well, the type, in this case, this array is a double, right? So we say this is double, and we're specifying the type parameter for this template, and so that we're just helping out because the compiler cannot deduce it. Now, so we'll get another error, which is a line below. That means this fixed this line. And this is the same problem, actually, and the same problem for all those lines. So we're going to just fix this everything here. And this is int, right? Because these numbers, they are ints. This is basically, if you hover over these numbers, it's deduced into an int type. Okay. Now you may have noticed, by the way, you can ignore the __1. This is particularly what the information provided in the compiler. This is can be ignored. Now there's two parameters of this vector. There's int, there's an allocator. So I believe we talk a little bit about the dynamic memory management. So many of the containers in the standard library allow you to specify your own allocator, memory allocator. And so we're not using it. Typically, it has a default allocator. The default allocator essentially just uses the new and delete operators. So that is the default behavior. Now, unless this is something you want to manage, a pretty advanced technique here, and then normally you don't need to worry about it. So, but just know that this vector actually has two template parameters, and then this allocator has a default value. So the book also has a portion that talks about you can actually have a default value for your template parameters as well, just like your function parameters that can have default values. So for data those are double, and array data, that's also double. And names, so those are string views, right? Obviously, because that's the type that will specify string view. All right, so let's see if we fix that problem. Now we have helped the compiler determine what this template parameter is. Okay, looks like there's no more errors. Let's see whether we can run this thing. Okay, it works. Right, this result is the same as before. Uh, Now you might wonder, okay, is this yeah, this is working, right? Because look, I did not remove the or comment out the original functions, but they're not going to be even inspected by the compiler here because they're not even used. They're not using here in the sense that because we have not declared the declaration or the prototype are not declared here, so the compiler is not aware of those. So they don't really matter here. Okay, just in case you wonder, is it calling those things or is it using a template? Is it using a template? Okay. So that really kind of solves that code duplication problem that we encountered uh, in the last chapter. Okay, so this is why the function templates are useful. Um, the templates are used in the standard library pretty much everywhere. It's extensive use of function templates and also, of course, class templates. And we're going to talk about classes next week. Okay, so that's what I have to share about this chapter. Thank you.